Good morning. Can people, hopefully everybody can hear me. This is Scott Noland with RPI. I'm having a little bit of technical difficulty here. Here we go. Okay. Good morning, everyone. My name is Scott Noland. I'm with RPI. Want to welcome everyone to this webinar. I'm going to talk about activated carbon. Activated carbon has been around for a really long time. This is a picture just really from one of our early jobs, long time ago, back in the early days, like 2002. And so it's a little history. The person there on the left, that's a much younger version of me. And the person on the right here is actually Matt Steer, who's one of the owners of Alpine Remediation. And you can tell we were having an awful good time that day. This was one of our very first Boss 200 jobs. The fellow in the middle, he's the only smart one of the bunch. That's Jeff Stearman, and he actually got out of the industry and is doing quite well for himself. So again, activated carbon has been around for a really long time, and over the years the industry has characterized carbon with a number of rules of thumb. Sorry about that. So one of those rules of thumbs is that people have said all carbons are the same. And in fact, there's an EPA white paper that came out several years ago where that statement was made. And yet, I can tell you that carbons are quite different. And as you can see, it's the raw materials that really dictate the ultimate properties of the carbon. So you can make activated carbon out of anything that contains carbon. So coconut shell and bituminous coal, lignite, wood, many other things have been used, olive pits. Each one of these things is going to have different ash, they're going to have different pore structures, they're going to have different characteristics. And they're quite different. So indeed, all carbons aren't the same. And some carbons perform much better than others depending on what your application is. One of the real powers of activated carbon is the fact that it can be used and then regenerated, so it can be reactivated. Virgin carbons are carbons that are newly manufactured from raw materials such as coal. Reactivated carbons, there's a huge segment of this obviously out there. There's probably not a potable water system anywhere in the country that doesn't have at least one carbon bed on it somewhere. So there's really two segments within the reactivated carbons. There's drinking water and there's wastewater. The drinking water carbons are really well managed because they're essentially resold back to the original customer. As they lose some of the carbon through the reactivation process, they supplement that with virgin carbons. So that housekeeping is really good. On the other side of the coin, the wastewater side, the housekeeping is very poor. It's just, there's food grade carbons and then there's everything else. The problem with that is that the reactivated carbons can have a potential for heavy metal contamination. There's no potential for any organic contaminants to still be in the reactivation. They all get burned away. But the inorganic things, the heavy metals, can persist after that reactivation. So one thing I would say to everyone out there is never use reactivated carbons for in-situ remediation. And I know a number of years ago, there were a couple people out there that were kind of championing that cause, but not so much anymore. I want to spend some time on this slide because this concept is really important. And it's this idea of rollover. Adsorption in activated carbon is a thermodynamic process. And the heat of adsorption according to Calgon Carbon, for all organic compounds, that heat of absorption is exothermic. So it gives off heat. You can even feel it with just water. I was out in the field one time, and we were doing some test mixes in a soil mixing project. And we had 55-gallon drums of carbon that we were wetting with water, treating it as if it were the Boss 100 that we were ultimately going to put in the ground. And I noticed that the water was warm. So there was actual heat of absorption from the water itself. Anyway, coming back to the importance of this slide. So rollover is when you can have one contaminant that's absorbed to the carbon, gets kicked off the carbon by another one. And in order to illustrate that, we went in the lab and we looked at two different things, xylene and vinyl chloride. So we had one vial where I spiked in a certain amount of xylene, in this case 2000 ppm, as you can see, and the second vial was 100 ppm of vinyl chloride. Then we mixed it real well and we waited for equilibrium to take place, measured what was left in the water. So we now had 1.42 ppm of xylene in the vial, and we had 2.4 ppm of vinyl chloride. So then what we did is we took the vinyl chloride vial and we spiked it with 2000 ppm of xylene. After an hour, you could see what the concentrations were. Our vinyl chloride is now going up, and we still haven't come close to our equilibrium concentration on the xylene. We're still about an order of magnitude away. After 1 day, our vinyl chloride is now up over 16 ppm, and we're getting close to our equilibrium concentration. So why is this so important? Well, for a couple of different reasons. Number one is that large molecules, or any molecule that has a higher heat of absorption than something that's already absorbed to the carbon, can kick that off. So for example, if you don't have a good treatment mechanism in place to go along with the carbon, then you risk this displacement over time. So activated carbon could be used on a hydrocarbon site. You could absorb benzene, and then over time, it could bleed back off the carbon if you don't have a good treatment mechanism in place. So one of the areas where I've seen a trend in the industry of using activated carbon where there's no treatment mechanism is in the treatment of PFAS. And a couple of years ago, I think it was in 2016, at the Battelle conference in Palm Springs, Tim Appelman, who's with the Navy, was doing a platform presentation, and he made this comment that the Navy will not allow activated carbon to be used in situ on PFAS sites. The reason that he said that is because of rollover, because the heat of absorption of PFAS on activated carbon is very low, which means they can be displaced by all kinds of things. TOC is one of the biggest enemies of carbon beds. TOC will displace it. I know of almost no sites where just PFAS is the only contaminant. There's always other things floating around. Anything with a higher heat of absorption will kick the PFAS off. And so essentially what happens when you put activated carbon in the ground is you run the risk. It's more than just a risk. You create a new source for the PFAS that's going to come back off over a period of time. It's because of this concept that RPI has never allowed any of its products to be used on a PFAS site, and we never will. So moving on. One of these other rules of thumbs of activated carbon has to do with this idea of just absorption capacity. And I've heard countless people tell me that, well, activated carbon has the capacity to absorb 15 to 20% by weight of organic compounds. The fact is that the absorption capacity of activated carbon is, number one, a strong function of what the contaminant is. They're all quite different. And it's also a function of the concentration. And this is illustrated here with just this data from benzene and ethylbenzene. So you can see here at 1 ppm, if I had a source of benzene in water, the absorption capacity of the activated carbon And this is data that was taken from Calgon's F400 series carbons. Because remember, carbons aren't all the same, and this will be different depending on the carbon you're using. But in any case, with that carbon, you can see the capacity is a milligram per mil, or per gram, I'm sorry. Ethylbenzene, on the other hand, at that same concentration, is 53 milligrams per gram. It's over an order of magnitude different. And when you look at 10 ppm at the benzene and the ethylbenzene, we're still almost an order of magnitude different. But notice the ethylbenzene, even at 10 ppm, is already sitting at 32.5% by weight. And that's just at 10 ppm. And it's not saturated yet. So, and this is also an important concept. And where has it become really important? I can tell you that when it comes to LNAPL sites, for example, I've had Big Oil has always come back and told me, Scott, you can't use activated carbon on LNAPL sites. You can't put enough carbon in the ground because of this absorption capacity limitation. And they were thinking along those lines of the rules of thumb. So one of the things that we did here at RPI is we went into the lab and we took a couple of different carbons. We took the activated carbon from Calgon that we use in our BOSS 200, and we also tested some wood-based carbon, because if for anybody who's looked at a photomicrograph on wood-based carbons, it's a very unique kind of structure. It's almost like a beehive. There's cells, and so for that reason, I thought it would potentially absorb tremendous amounts of LNAPL. So in this case, we're looking at diesel. So we carefully measured the absorption capacity of free phase diesel fuel in water saturated carbons. This is the result that we got. So in the coal-based carbon from Calgon, we saturated at 58 weight percent. The wood-based was disappointing at just half that number. So the industry was wrong in terms of the rule of thumb on the absorption capacity, but they still weren't thinking about this right, because even at 58 weight percent, you still can't put enough carbon in the ground to just use carbon to absorb all the mass on these LNAPL sites. From day one, RPI has always said the carbon cleans the groundwater, the bugs clean the carbon. It's kind of a catchy phrase. Carbon cleans groundwater, the bugs clean the carbon. Pretty soon, our competitors started to use it. So everybody out there is saying the carbon cleans groundwater, the bugs clean the carbon. Industry said the bugs are too big. And they're right. Talk about throwing cold water on a concept. The microbes are too big. They can't get into the microporous structure of the carbon, and that's where over 90% of the absorption takes place. So this concept of the bioavailability is another really important issue. It's a burning question out in the industry. So remember that carbon that we loaded up with diesel fuel? We then went into the lab and we took that carbon and we conducted a bench test on that carbon, preloaded with diesel fuel. Sometimes the things that you can just visibly see are very informative. So here's a picture of some of the vials that we used in our diesel bench test. You can see that we've got some vials that are yellow, some that are pink, some that are colorless. For a long time, we've all understood that trace metals in the subsurface in the dissolved phase are good electron acceptors. And so, at least I believe, in all of the vials here in our test, of course, had trace metals added to them to support the biological activity that we were trying to measure. And so I think that the yellow coloration is probably due to iron changing valence state. And the pinkish is either cobalt or manganese, both of which were in the system. So again, and this is not a real surprise because we all knew that metals can participate in these kind of reactions. And electron transfer, of course, is at the heart of the biological degradation of these compounds. I love this slide. This is an actual picture from, again, one of the test vials in this diesel bench. And so you can literally see, talk about biofilm. We have massive formation of biofilm here. In fact, the carbon is just in this glop of goo. The consistency inside the vial was like egg drop soup. It's pretty thick. And you can actually see evidence of just the goo all around here. And all the gas bubbles that are evidence of biological activity working on that diesel that is in the pore structure of the carbon. So we need to think about ways in which these things are bioavailable, ways that the bugs can somehow or other get to those things that are in the pore structure of the carbon. And I'm not a microbiologist, but I do know that, for example, microbes secrete enzymes. Enzymes are large molecules. They have high heats of absorption. They can get into the porous structure and displace things out where the waiting microcosm is. The bugs can, in fact, inhabit the macro and mesopore structure in activated carbon. So they can get close, they just don't have immediate contact down in the microporous structure. So here's some of the data that was generated from our bench test. And you can see that here's the, I got ahead of myself here. On the right, we have the mass of the diesel fuel in terms of total milligrams. So the dose of the carbon that we added into our test started out with approximately just over 180 milligrams of total diesel fuel was in the carbon. And then over a period of 6 months, at various times, shown by the little dots here, we took samples and analyzed both the water and extracted everything that was on the carbon to find out how much diesel fuel had been degraded over that time. And you can see the graph here. The image of the graph or the shape of the graph is very important because in most kinetics, degradation kinetics, in fact, we commonly use first order kinetics to model all kinds of different systems in the environmental industry. First order kinetics are, as you all know, exponential. It's not a straight line. This is a straight line indicating zero order kinetics, which says that the rate of degradation is independent of the concentration. And you can see here's my linear regression for the line. So this number right here is the slope. What that slope is telling us is that this is the average mass removal rate per day in terms of milligrams of diesel fuel. So what is this graph suggesting? This graph is suggesting that there's a linear relationship between the rate of degradation and the total surface area of the carbon that is available. So activated carbon is a platform. The platform supports the degradation. The larger the stage or the larger the platform, then the more rapid the mass removal can be. So in LNAPL sites, natural source zone depletion has gotten an awful lot of attention. And back in 2017, we took this information from the diesel bench because it opens up an entire new way to look at design for treatment of these sites. Rather than looking at carbon demand and asking, can I put enough carbon in the ground to just absorb this stuff? Now I can take advantage of kinetics and back into a timeline to say, what's the mass? And when do I want that mass to essentially be degraded? And on a diesel LNAPL site, the most important feature is just elimination of measurable LNAPL in the groundwater, because there's really not a lot of VOCs that are much of an issue. So if I can get rid of the LNAPL, I'm in pretty good shape. So in 2017 in Texas, we took this and we applied this on a site, a condensate site. We actually began the injections on the site in July of 2017. I want to take a step backward just for a second. And this slide, I'm going to come back to this site just momentarily, but I need to set the stage for the mass removal. This slide came from a recent ITRC guidance document on LNAPL. And so you can see that over here on the right, we've got the depth to the aerobic anaerobic interface, and we have these mass removal rates in different units on the horizontal. So the lines here, we have clay on one end, and we've got sand, gravel on the other side. So when you look at this interface, I mean, how many hydrocarbon impacted sites have we looked at where we really see the interface somewhere down around 10 feet, well, certainly between 10 and 20 feet. And, we have soils that fall in this area here. So really, most of the sites that we look at probably fall into this central area. And the site that we worked on in Texas falls in this central area. And so in order to compare data, what I did is I chose a number kind of in the middle. So right here, this would be 2 grams of mass removal rate of 2 grams per square meter per day. So using that number, which would be predicted for the natural source zone depletion, and then looking at what happened on the site. So how does it stack up? So remember the natural source zone depletion, mass removal rate, the 2 grams of free phase per meter squared day. When I translate that into this site, that becomes 730 grams of free phase per meter squared year. Now, through sampling on the site, we estimated what the mass removal rate was on this large condensate site. And the number that we estimated was approximately 5,065 grams of free phase condensate per meter squared year, roughly 7 times higher than what the natural source zone depletion would be. So the point here is that activated carbon absolutely can play a role on these LNAPL sites, and that you don't have to worry about the limitation that I can't shove enough carbon down into the ground. There's another way to look at these sites, and the way to look at them is from the kinetic side of things, and look at designing a certain stage size to get the mass removal rate you want to eliminate the LNAPL over a certain period of time. So this is just a summary of just applications of free product. And this site that I just talked about, as of September of 2019, and I can tell you that our kinetic design was based upon elimination of LNAPL in about 2 years. So from July of 2017 to September of 2019, that's just over 2 years. So out of 20 wells that are in the footprint of LNAPL at day 1, as of September, 2 have measurable NAPL. One of those wells of the 2 is in an area where we literally couldn't get access. And so I know that particular well is going to take a long time to clean up. So we also have 11 of those wells, which not only do they not have any NAPL, but the benzene is now below MCL. And the condensate on this site in Texas was quite high in benzene. So, I mean, it was almost like having gasoline in the ground. We can, in fact, use this same approach on the design to deal with LNAPL gasoline. And in fact, although we didn't apply this particular approach on the design, this site in Denmark, we did have 1 to 5 feet of actual gasoline in monitor wells. Anyway, coming back just to finish up on this site in Texas, 6 of the wells do suggest that we still have submerged NAPL. It's just a suggestion, and that's based upon the benzene concentration that still persists in the water, where we have greater than 50 parts per billion. And we, again, use site data to estimate at what point the groundwater concentrations of the contaminant would begin to suggest that we had submerged NAPL. In total, we've treated roughly 50 LNAPL sites, and about 60% of those are closed. So the site in Denmark was a gasoline site. That one was heavily impacted with LNAPL GRO. And from the pilot test through 5 years, this site did receive an NFA in Denmark in 2018. So I want to come back and say a little bit more about bioavailability, because this is such an important concept. And carbon is a conductor, and I'm going to talk about the importance of that in just a second. But the idea of bioavailability and for things absorbed on activated carbon is not a new question, nor is it a thing that there hasn't been information speaking specifically to that question in the past. For anyone who's interested, I have a set of peer-reviewed articles that date from 2004 to 2017 speaking directly to this question. So for example, in 2004, and this involves Carey sublet and bio beads. And the biocep beads are a polymer bead, but there's also powdered activated carbon in the biocep. And in 2004, there was an article that was co-authored by Aaron Peacock in Microbial Technology, and it talks about the degradation of things that are absorbed on there. There's additional data from biocep where we actually loaded the biocep beads with carbon-13 labeled benzene, and then using carbon isotope analysis, we're able to show specifically the degradation of these things. In addition to that, Derek Lovely wrote a review article in 2017 talking about this idea of direct interspecies electron transfer, DIET for short. I bring this up because RPI is hosting a number of webinars, as you know, and the webinar next week, Tuesday, we have a guest speaker, and that guest speaker is Aaron Peacock. Aaron Peacock is the author and co-author on some of these references. He's in a position to know about how microorganisms function with activated carbon and how they enhance one another in terms of the performance. The bugs don't have to actually touch the contaminant. They don't have to get into the micropore structure. Electron transfer can take place without them touching it. And Derek Lovely in his article did point that out. This DIET, direct interspecies electron transfer, that Aaron's going to talk about more on next week, Tuesday. He mentions in the article early on that organisms don't have to transfer electrons to other organisms. They can transfer electrons to activated carbon because it's a conductor. Another application of this concept is activated carbon that's impregnated with iron for degradation of chlorinated solvents. And one of the big limitations would be the iron demand. So the iron is oxidized in the process of this reductive dechlorination. But when you marry the technologies, biological with the abiotic, it's the heart of our CAT 100 technology. Now the carbon can actually shuttle electrons. And I've got this little bit of just rough animation to kind of show you the concept. So I've got a molecule of TCE that's absorbed to the iron, and I've got electrons being shuttled to the iron so that the TCE can be degraded. Here's a larger image of that. Dr. Finneran at Clemson University published a paper on activated carbon shuttling electrons to RDX and the degradation of that occurs. So the point of this is the bugs don't have to get into the pore structure. They can take electrons and put them into the carbon, or they can take electrons out of the carbon. So there's two different pathways where these things can happen. They secrete enzymes. So there's multiple mechanisms for how these organisms can get at these absorbed contaminants. So I would be remiss if I didn't say something at least about injections. Injections are very surgical, and the state of Kentucky, GeoSierra, RPI, and Arcadis were actually going to teach a class at this year's Battelle conference in Portland And unfortunately, as we all know, the conference was canceled. The course was just gonna focus on injection of slurries, of which a lot of these products that use carbon-based injectates, they're slurries. RPI, all of our products are slurries when they're injected in the ground. And injections are very surgical. So here's some actual data from a chlorinated solvent site that was here in Denver. And you can see how the concentration of TCE is changing as a function of depth. And you can see the changes in depth here in this complex lithological setting where we've got silt and clay interbedded is changing very rapidly over very small distances. We're talking about a couple of centimeters here. And look at the change in the concentration. I mean, from 11.6 to 11.66 to 0.72, this concentration went up by almost 3 orders of magnitude. This is 2.5% by weight of TCE in this thin little zone down here in the silt. Over here is a monitor well from that site, and it's screened across this zone. Originally, the plan was to go after this with oxidants, permanganate. Pretty good idea. But if the data wasn't this high resolution, if you didn't know about this zone of really hot TCE and the amount of mass that was there, you'd be injecting permanganate forever, trying to clean up this site. So I guess one of the things I want to close on is the fact that the additional data collection supporting your in situ remediation, and this was actually talked about in a brand new guidance document at ITRC on injections, where they actually used the phrase remedial design characterization and have talked about the value and the power in collecting soil samples, for example, from below this, in the saturated zone, below the water table, to really determine the distribution of contamination on your site. That data is crucial to successful in situ remediation. Okay, on that note, I'll close and open things up to questions. My phone number and my email address are here on the slide. I do apologize for my difficulties on the front of the presentation. But in any case, people who have want to talk to me or ask questions, as I said earlier, anyone who's interested in copies of these articles from the peer-reviewed literature that I mentioned some of, just email me and I'll be happy to send them to you. Jim, if you're out there, I know you're very interested in biofilm, and one of those articles did concern biofilm, and I will go ahead and send it to you. Okay, let's see. So again, I want to just point people to some of the other webinars that are going to be taking place while I sit and wait a couple minutes for questions that might be out there. Carbon is just a really powerful material, and it needs to see more and more use across the environmental industry in remediation. There's been a lot of misinformation out there. I've had people suggest that activated carbon is a great adsorbent for metals. The fact is that activated carbon in general is not very good for charged species. So that includes anions and cations. So for example, if you look up the performance of something like phenol for adsorption at acidic and neutral pH, it performs quite well. But if the pH gets too far basic, then you get the phenolate anion, and now the adsorption just drops through the floor. It's not real good with charged species. There are specialized carbons that have been treated for things like gold, for example. So there are exceptions, but in general, activated carbon doesn't do well with cations and anions. the next presentation, which will be by Aaron on Tuesday, is I'm really looking forward to that, because the whole discussion is going to be about bioavailability and the ways in which the microorganisms work with activated carbon to enhance the capabilities of each of those two things to achieve results that can't be achieved with either alone. Okay, well, I certainly enjoyed talking with everyone. I look forward to getting some emails and phone calls. I'll be happy to talk to people offline. I appreciate your attendance. And it's been a... I've got more. Oh, hang on. I guess there's some more questions. So I was about ready to sign off. Oh, okay. I apologize. I've got a number of questions, so I'm going to hang out here for a minute and see if I can start to get to some of those. Bear with me. We're just trying to get them organized here.
That's the first one.
I think one of the questions was early on, which had to do with whether or not I would expect the same dynamics with gasoline LNAPL as I saw with diesel. And I think I actually already kind of talked about that, because I said that we've seen a similar dynamic with gasoline. Although I have to admit that we haven't actually applied the kinetic design yet to a gasoline LNAPL site, but I have no doubts that it would work fine. Another question had to do with how did we determine the adsorption capacity? For the diesel fuel, the way we did that was we took our 2 samples of carbon and we put them into a 1 liter bottle, and we added about a half a liter to 3/4 of a liter of water, and we then mixed those things for several days so that we could totally saturate the carbon, the pore structure. Then what we did is we came back and we added some diesel fuel, an excess of diesel fuel, to those bottles, and we put them back on our rotator and we mixed them for several days so that we could again achieve an equilibrium. And so then what we did is we recovered the carbon. So we vacuum filtered it. We washed the carbon with cold methanol to get rid of anything that might have been on the outer surface. And then we took those samples of carbon and we extracted it so that we could analyze how much was on there. So we did it by analytical. But anyway, that's how we did that. Let's see. So another question is, what would I use for PFAS if not activated carbon? So activated carbon is actually the best available technology for work on PFAS sites, and we're all aware of that. The key is it's not in situ, it's above ground. And so it's a pump and treat, it's a mechanical system, and it is the best technology. And in fact, the carbons can be regenerated. So that's what I would say that we should be using at the moment. There's a lot of really smart people that are working on this issue. And I mean, RPI is working on it, everybody's working on it. So far, we haven't got a good practical way to degrade these things in an in situ treatment. There's lots of different kind of chemistries that have been looked at. Some chemistries are successful in the lab, but we're never going to get those kind of conditions in the subsurface. Unfortunately, we're not in a position to issue a certificate of attendance. Is that correct, Bob? Yeah, I'm sorry. So I wish I could do that, but we're not able to. There was another comment from a person who has a site with salinity on, it's a coastal environment. And I can tell you that we've used activated carbon in a lot of different scenarios. We've used it on, for example, at Vandenberg Air Force Base, where we were about a quarter of a mile from the beach. So we've used it in situations where the TDS and the salinity is very high, and as has calgon carbon. And the salinity and the TDS doesn't interfere with the properties of the activated carbon. Someone else submitted a question regarding to methane that forms during biodegradation. And there was a Clemson study. I'm not quite sure. There's been a number of studies. I'm not sure which one. You might have to email me or give me a call to be a little bit more specific. We, within RPI, we do support all of our projects with free analytical. And one of the capabilities that we have in the lab is to analyze for low molecular weight hydrocarbon gases to include things like methane, ethane, acetylene, propane. We're calibrated for 13 different compounds. So we actively measure the methane, these gases, not just on chlorinated solvent sites, which was where we first started looking at, and we got the instrumentation for that reason. But we had it, so we started looking at hydrocarbon sites as well. And there are some very characteristic fingerprints of gases that are generated. We've done work with EZVI to look at the kind of signature that generates. So we do a lot of that kind of work, and we see methane. Methane's ubiquitous. It's almost everywhere. You're going to see a small amount of methane no matter where you look. However, there are some things that we've learned about methane and how to control methane, more so on chlorinated solvent sites, I think, than on hydrocarbon sites. The other thing that we've added this year that I believe is really important is the fact that we can also get CO2 data. So we can get CO2 concentrations in the groundwater on these sites. And that's more important on the hydrocarbon side of things, at least I think, than on the chlorinated side of things. So we have to be careful to take the analysis out of a non-preserved vial so that we don't get any high bias because of inorganic carbon. There was another question, a lot of questions, it's really cool. Another question, someone wanted me to talk a little bit about change in subsurface dynamics caused by carbon seams and beds when carbon is more coarse than the geological material. Okay, so the Boss 200 product of RPI is really, looks like black flour. It's very fine, 300 mesh or less. Our Boss 100 product is a granular product made from a 12 by 40 mesh food grade carbon. In fact, I should say all of our products are made, they're virgin carbons. They're all food grade carbons. They're the highest quality. We've never used any kind of reactivated carbons, and we've never used anything but food grade carbons, and we never will. Anyway, the 12 by 40 mesh is granular carbon. It looks like it's a little coarser than the sand that you put in around monitor wells for the filter pack. And I can tell you that, at least in large picture, the hydrodynamics or the hydrogeology of sites, we haven't really seen measurable changes, at least I haven't. And my background is chemical engineering. And I know that a lot of people think that when you put material, particularly a coarser material in like in a fine-grained soil scenario, that we now create preferential flow paths. But the one thing that I would point to is that, just do a thought experiment with me for a minute. If I went to a site, and let's say it was a clay site, and I could somehow or other instantly create a void down in that space, say a pipe, and that pipe is an open pipe and it's just a void. So clearly that would be a preferential flow path. And initially, water would accumulate in that pipe, and it might even preferentially move in that direction. It would disturb the flow net on the site. However, once it's full, equilibrium sets in, and now the flow nets, the original flow net, will reestablish itself. And so unless there's actually a discharge path for things to follow, you're not going to see any kind of a preferential flow path be created. I can tell you that the one thing you can say about injections, whenever you do pressure injections into a subsurface environment, when you start forcing things under pressure into the formation, it's always going to take the path of least resistance. And so if you've got bedding planes, if you've got sand lenses that are interbedded with silts and clays, you're going to find those things and you'll have preferential flow. We have an actual presentation associated with a project, a very special project we did with the state of Kentucky, where it's really an R&D type project, where we sampled the site to death. And when we actually went out and treated the site with Boss 200, we went, like a month later, we went back out there and we took over 40 soil cores within the treated area and logged them very carefully to see where carbon was and where it wasn't. You can learn a tremendous amount about distribution and what happens when you inject things under pressure by looking at the photos and looking at that presentation. If that's something people are interested in. Unfortunately, the animation is really, it's quite intense. It doesn't work well on a webinar scenario, but we could certainly come to your office and show you that presentation. There's some really cool information in there. See, here's another comment. If the bugs in the subsurface eat the contamination, then the carbon kinetics would release more contaminant in a game of musical chairs. That is, the bugs don't need to get into the micropore space. If I understand the question, then my point on the bioavailability is that they don't need to. I think people tend to believe that it's a contact sport. If the bugs can't actually contact the food, they can't take advantage of it. And I think that you'll learn, for all of you who are interested in this question, please attend next week's webinar. But we've found from a lot of research that's been done spanning a couple of decades that the organisms don't have to actually touch it. There's ways that they can benefit from it long distance. And they can utilize things like carbon. They can utilize this direct interspecies transfer of electrons, this concept of diet, if you will, that was spoken about by Derek Lovely. So you're correct. They don't have to actually get into the microporous structure. They can be degraded, and RPI has tons of data to show that there is degradation that takes place on the things that are on the carbon. Chlorinated solvents, gasoline, diesel. We've got a ton of data. So please contact me. We'll be happy to share those things with you. Someone else sent me a comment where I had talked about submerged LNAPL and suggested that it was a problem. The only reason I suggested that it was a problem is, as we all know, the presence or absence of LNAPL on a site is it's directly correlated to the depth of groundwater. So when the groundwater becomes really shallow and it submerges the LNAPL, then we don't see it in the wells, and it gives us this false sense of security that, oh, well, the LNAPL's gone. Then when the water table falls, then all of a sudden, miraculously, the LNAPL is back. And so this site that I talked about in Texas, the groundwater has gone up and down, and to be honest with you, as I sit here this morning, I can't remember in September exactly where the water table was with respect to elevations where LNAPL was commonly visible. But I can say that in the past, when the water table was high and we were able to look at the VOCs dissolved in the aqueous phase and then use that data to predict when the water table fell, which wells would have NAPL and which ones wouldn't, the correlation that we got was pretty good. So that's why I pointed that out on this site, where we have a number of wells where we have no indication of LNAPL, no matter where the water table is. We've got benzene below the MCL. And we do still have, the one well in particular that has measurable NAPL on it. And we have 6 wells that we think, if the water table fell far enough, might exhibit LNAPL. So we haven't closed the book on this site yet. The remediation is still in progress. I received a number of people just thanking us for the presentation. We're all getting through a really difficult time. So anything we can do to break it up and pass along some information at the same time, we're happy to do that. So it was a pleasure to talk to you guys today. I can see that a lot of you are still online, and I've used up way more of the time than I originally planned to. I thank all of you for the time that you spent. One other question, and then I think I'll try to sign off. There was a question regarding viscosity data on products like Boss 100. Viscosity in that case, and particularly with slurries in general, unless you're involving a thixotropic agent like Wargum, the viscosity is really just the water. If it's a water-based slurry of solids, Boss 100 is that. So we have to mix it all the time to keep it in suspension. So the viscosity is really the viscosity of water. But injecting those things, there's an art to it, and it's not easy. So it takes special techniques. The Boss 200 is more forgiving just because it's so fine. And again, viscosity doesn't really start to raise its ugly head until just the solids density. The slurry densities are approaching just the maximum amount of carbon you could put in a gallon of water, which is around 3 pounds per gallon. So then it starts to get not necessarily viscous, but it starts to get thick. It's like mud. Anyway, thanks once again for all of you out there who stuck with me through the difficulties in the beginning. You all have a wonderful day. Stay safe, stay healthy, and I look forward to further discussions. Let's see here. How do I kill it?